Section 2.2 is going to continue our discussion of sets. And what we're going to do in this section is we're actually going to create some imagery for what sets can be. So if you're a visual person, you might like this section. I like this section. I think very visually about things, right? Passcodes and stuff like that. I know the code based on where the numbers are on my husband's door to his office. That's how I know the code, right? Some visual, all right? So Venn diagrams are what we're going to be talking about. You may have seen Venn diagrams before. They are taught. They're not always taught with the same purpose in mind, but my daughter, Abby, who is a sophomore in college, she saw them for the first time, I remember, in second grade, okay? She didn't do quite what we're doing with them, but that's the first time it was introduced to her. So you may have seen these before. So Venn diagrams are drawn with a rectangle. So you start with a rectangle. And inside of the rectangle are circles. So this is a very basic Venn diagram. The outer box is the universal set. It's usually called U. So our box is the universal set, U. And the circle inside are any of the sets that we're describing. So we'll call it A. Sometimes I label my circles by what they're describing if I'm actually working with a problem that has context, okay? So our circles in general are other sets in the universal set. A smaller collection. For example, we encountered one of these, we didn't describe it this way, we encountered one of these in the last section when we talked about even numbers, right? Even numbers, especially if we're only talking about positive ones, are a collection of the whole numbers. They're a collection inside of, they're a circle inside of the natural numbers, those kind of things. So it's a smaller grouping inside of the larger grouping. So in this classroom, if you guys were the universal set, we could have a circle inside of there for girls, for example, right? That would be a collection that's smaller than the whole group, right? The complement of the set, A, within the universal set, is simply all the elements that are not in the circle. Right? So if my circle represents A, like it did on my picture, then the outer part, still inside the rectangle, but the outer part would represent the complement. The notation that your book uses is A with a prime on it. That's not the only notation for complements. Sometimes complements have a bar on the top of them. So another book that I use does complements like that. And that's another common notation. A third common notation is actually a little C in the superscript, right? Like kind of an exponent spot, A complement. So if you were to see any of those listed somewhere else, that's the same thing. Now the notation for this looks a little bit like things we were just doing, right? The description here says A complement is the set X, such that X is in the universal set, so it has to be in the box, but X is not in the circle A. So in terms of a picture, that's not what I meant to do. That is. If we have set A and the universal set U here, then the complement is this sort of, it's not circled, so it doesn't exactly look like a donut. But it kind of looks like a donut, right? It's the part around. That's what a complement is. It's exactly the opposite of whatever's in set A, or at least whatever's not included. So we could make the circle A in our circle upperclassmen in this class, right? There's a few of you because I got your papers. So if you're not a freshman, you would be inside the circle. Everybody else would be inside the rectangle part outside of the circle, right? Because it's one or the other, right? There's no gray areas on that. Okay, so when we're looking at examples, we can do this with lists of things as well. So we're going to take the universal set that's the numbers 1 through 10, right? The natural numbers 1 through 10, counting numbers. And the set A that we're given, we'll call it A. It's not listed here, but this is set A, right? Is the numbers 1, 2, 3, 4, 7, and 10. So if I want the complement then, I need to list everything in the numbers 1 through 10 that's not included in that list A. What would it include? 5, 6, 8, 9. Is that okay? Right, that's what it would be. Now, you could do that with lists of numbers and it's going to work the same every time. Number 2 looks weird though, because number 2 is the set U. So this actually feels a little bit funny, but we've seen the complement of this before. So very literally, what this is saying is I want the complement of the set of numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So I want everything within the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 that is not 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And what would that be? Nothing. And we have a notation for that. Do you remember what that looks like? Yeah.
The circle with the thing through?
It is. It's a circle with the line through. Good remembering. Okay, so the complement of U, because that's the one we actually were given, is the empty set. It's the set that has nothing in it. Because if I take U and I make that my entire universe and I want the complement of it, there's nothing left. So this would be the empty set. It's also true that if I had the empty set and I did the complement, I would get the universal set, by the way. Right? They're pairs. They're pairs, they go together. Those do come up from time to time, so just be aware. You're going to get a question probably inside of your homework, maybe inside of your quiz, that's going to ask you something about either the U or the empty set, and you should just know them because they always are the same. It doesn't matter what U is. If they're giving you the complement of it, it's going to be the empty set. Okay? All right, now we've mentioned this, at least I mentioned it, I didn't describe this word. Subset. Subset is a set that's contained inside of another one. So in some sense, the A circle is already a subset of the universal rectangle, okay? But this is actually talking about circles that are inside of one another. So a set A is a subset of B if every element of A is also an element of B. The notation is that A, we read this, is contained in B. So contained in means it's inside of. So here's circle A. And it's supposed to be inside of circle B, the way that that's described. And all of this is inside of the universal set U. So that's what a subset looks like. It's an embedded set. We drew this in 2.1. Do you remember my rectangle that had the rectangles inside of them? Most of you are saying yes. Some of you are going, no. Look back at your notes. They're there. We had rectangles. We didn't draw circles. I drew them as rectangles. But it had the same properties, right? I had this little box in the middle. It says natural numbers, and then I had a box around it that said whole, and I had a box around it that said, integers was next, and then I had the half side of it being the rational, and then the whole rectangle being real. Remember that? That's another way of drawing them. It's not the typical way of drawing Venn diagrams, but it's the same idea. We had these embedded categories. I mentioned in section 2.1 that we would look at another definition of set equality. That's this one. So our definition in 2.1 was that every element of A was an element of B, every element of B was an element of A. If that happens, then the sets are equal. Another way to describe this is that they're equal if A is contained in B and B is contained in A. But that's what it means to be a subset. It means that it's contained in. So A is contained in B and B is contained in A. It just means that we're talking about the same set. So if I were to talk about my family, right, like they get together on Christmas morning, we're going to go with that. The family gets together on Christmas morning. So my husband and my children, and my husband were to talk about his family that gets together on Christmas morning. We'd be talking about the same group of people, right? Same group of people. Those are set equality. Now, a proper subset means that it's actually smaller inside than the bigger one. Now, we kind of think that's what we mean by sets that are subsets anyway, but it doesn't have to be, right? So if I describe my family gets together on on Christmas morning, that's a subset of my husband's family that gets together on Christmas morning. They're the same, but by definition, it's a subset because every element of my family is an element of the family he's describing to. Okay? That's not real exciting. Like, why would we want to describe it that way? But it fits the definition. And because of that, we want to have a little bit more strict definition that makes things a little clearer. And this is what it is. It's called a proper subset. Notice the difference right here is that it doesn't have the line underneath it in terms of notation, right? So this kind of harkens back to the idea of less than or equal to's as well. Right? When I have the line underneath it, it means it could be equal. It doesn't have to be, right? The number 6 works for x in either case. Yeah? It doesn't have to be equal, but it could. Whereas the number 7 actually fits the description on bottom. A little weird. You would say 7 is less than or equal to 7, and you'd be like, I mean, yeah, but why would you say it that way, right? It's a weird way to describe it, but it fits. Whereas 7 is not less than 7. It doesn't fit at all in the first description. That's what this is doing. That line underneath it means it could be equal. The two sets could be the same, but if the line's missing, they cannot be the same. It's not possible, right? So let's take a look at some examples of this. All right, our directions are going to ask, this is like a multiple choice. This is how it'll show up inside of inside of My Math Lab as well. It'll ask you to give one of 3 things, and I think it'll show up like a drop-down menu where you select one of the 3 options. It'll say to either select the subset notation, that's the one that has the equals underneath it, the proper subset notation, which is the one that doesn't have the equals underneath it, or there'll be an option that says this or this. It's both. Both of them could go in there and it would be good to go. So we actually can't just decide this is the answer and move on, because it might be the answer both, right? Like it's like when there's all of the above things on a multiple choice test. We have to actually check each of the choices and see which one's the best choice. All right, so on the left, I have the set B, C, D. And on the right, I have the set B, C, D, F. So issue number 1, is everything on the left also on the right?
No. Oh, yes.
Yes. Okay, the other direction's not, right? I can't go from left to right, but I should be able to go from right to left here. Everything on the, I said it backwards then too. Then I was getting myself confused. I'm so sorry. Okay, everything on the left is on the right. Yeah? B, C, and D, they're all there, okay? So I can put one of those 2 symbols in between there. I don't have to put the one neither. I mean, neither is not going to go in the blank. I've eliminated this option on number 3. That's what I've done. The next thing I have to decide is the set on the left smaller than the one on the right? It is, right? There is something left out. On the left-hand side, something is left out that's on the right. So that means that I actually have the ability to put the symbol, like so one symbol that could go in here is this symbol. It's truly smaller, right? You agree? Yeah, it's truly smaller. So this symbol could go in that blank. But this symbol just means that it's smaller or equal to. Is it smaller or equal to?
No.
It's an or.
Oh, is it?
It is, right? It is smaller or equal to, because it's an or. It's not an and, it's an or. It is smaller or equal to. So both of these actually fit in that blank. You might feel like, well, why wouldn't you just use the first one? Well, you could, but we're trying to give the best answer possible that includes the most options, right? Both of these fit in this blank. It is a subset. Everything on the left is on the right. And it actually really is smaller. So I can use the one without the equal sign. So I can use both of them in that blank. Let's look at number 4. Is everything in the set on the left contained in the set on the right? Yes. Okay. So I probably should have shown us this way, and so we'll do it this time. It is contained, right? Everything on the left is on the right. Again, neither is not an option right now. This one works. It's a subset. Is the set on the left smaller than the one on the right? No. They're exactly the same, right? They're exactly the same. So I can't put this symbol in here. It doesn't work. Because this is the symbol that means that it's truly smaller on the left. I don't have that option on this one. Now, if I had an option that was just said equals, that would be an option too, right? They are actually equal, but that's just not one of the 4 options I have. The 4 options say subset, proper subset, both, and neither. Those are my 4 choices. So it doesn't matter that there's a better description maybe that we like a little bit better. The one that we have at our disposal is this one. So if the sets are actually equal, you're using the subset only notation with the line underneath it. All right, how about on this one? Is everything on the left on the right? No. So what's going to go in this blank? Neither. It fails from the get-go, right? There's something. What is it that's included on the left that's not on the right? -1. Yeah. So inside this blank, I don't have much space. Maybe you don't either. It's neither. Neither of these symbols can go in this blank. Okay, the last topic in this section has to do with the number of subsets. How many of them are there? Okay? So when we have a small group of something, we can actually talk about this and we could list them out. So that's what I'm going to do first. We'll get our definitions written down and I'll show you that it works in a specific case. So this is definitely not a proof, but it's an example to justify. So for a set with n elements, there are 2 to the power n subsets. And there's 1 fewer proper subsets. Yes. N is the elements. Yep. So n is the number of items in the set. 2 to the n is the number of subsets we can make with them. Okay, so I'm going to show you a real live example so you can see what it means to create something like this. And we're going to use my colleagues. So you probably have not met them, most of you, but in the math department there are 4 of this, okay? And I'm going to use our first initials to identify. So my name is Krista, it's K. I have a colleague, Sarah Marsh, so that's an S. I have a colleague, Cherith Tucker, so that's a C. And I have a colleague, Nate Drake, which is an N. Works out nicely that they're all different letters, okay? This is my set. So we'll call this the set M for the math department. And the first thing I'd like for us to find is the cardinality. Now remember, cardinality means how many there are. How many are there? 4. There's 4. So according to what we've seen on the top of this screen, I should have 2 to the 4 subsets, and I should have 2 to the 4 minus 1 proper subsets. That's simply applying the definitions with the formulas I'm given, right? What is 2 to the 4? 16. And then the second one would then be 15. So that's what this tells me. But what is it actually finding? So I'd like to show you that. So imagine that we had a department meeting. We did this before school started. And within our department meeting, the department chair, that's Dr. Tucker, said, we're going to create some committees to do some different things. Okay? So committees usually mean they're a smaller group of the people you already have, right? So if I wanted a committee in this classroom, maybe I would let 5 of you be on the committee or something like that, right? 2 of you on the committee, whatever. So it's a smaller group than what you normally have. Now, if we do that, we could have lots of different kinds of committees. We could have committees that just have one person on them. We wouldn't call them committees, but we could have a collection of them that were just one person on that. You know, one person's assigned to do something. So we could have the subset that has just me in it, or one that has just Sarah in it, one that has just Cherith, or one that has just Nate. All of these are subsets of the universal set M, right? It's a smaller grouping. They seem kind of funny, kind of like the one I showed you back in section 2.1 that had the 7 in the curly braces. They seem like they're kind of funny, but by definition, they work. Everything in each of these individual sets is in the set M, right? Okay, so they're not an element now, the way that they're being written. They are a subset. But maybe it makes more sense to put 2 people in one of these groups together instead. So we're going to write all the ways we could do that. Well, we could have K and S together. We could have K and C together. We could have K and N together. That's all the pairings that have K in it, right? I could have, keeping on with my list, S and C, or S and N. And the last pairing of 2 would be C and N. These are all the groupings of 2, right? All the different ways I can group 2 people into a set. Okay, so I've done sets that are 1. I've done sets that are 2. What's the next thing I'm going to do? Sets that are 3. So I'm going to put 3 people in a set. So we're going to try and keep the order the same so that we don't lose people. We can do KSC. What else could I do? KSN. What else? SCN. And I'm missing one. Okay, I'm going to go with K first still to keep my order the same. KCN. Is that the one I want? Did I get them all? KSN, KSC, K. Yeah, I think that's all of them. There are 4 of them, right? Okay, how many do I have? We're getting close. How many is that?
16.
It's not 16 yet. It's 14. There are 2 sets that are missing, and they're the 2 that sometimes people forget about because, again, they feel like they're not really sets. At least they're not subsets. There's the set that has nobody in it. This would not be a very effective committee. Agreed? No. And then there's the set that's everybody. In this case, I called it M. There's the set that has everybody in it, right? The committee that is the math department as a whole. That's my 16. These are all the subsets of my set M. These are all 16 of them. And the empty set and the whole set are always included as 2 of those sets. Now, there is something to be said for the fact that the whole set doesn't feel really like a subset, right? So if I wanted to do, so these are all my subsets. And if I wanted to do the proper subsets, the proper ones include all of these. Except, which one? Which one's not included? Because I'm supposed to subtract one off. Which one's not included as a proper subset? It's not the one with nothing. It's the one with everything. Yeah. So remember, by definition, proper subsets have to be smaller than the set we talked about. Well, my whole set M is not smaller than M. It's exactly the same size. So by default, the empty set sort of like flies under the radar. He gets in there. He's skinny, he's not very exciting, he doesn't really do a whole lot. But by definition, everything in the empty set is in the universal set. Right? This is all those infants in my house. Every infant in my house is well behaved, if only the teenagers were. Right? Every infant in my house. It doesn't mean a lot because I don't have any infants in my house, right? But the definition still works the way it's set up. All right, I think we have two examples then with numbers, okay? So this is what it means to talk about subsets. So we're going to do some examples with values. So on this one, set number 6, we have the universal set, or the set, we'll call it A, the set A. And we're supposed to find A, the number of proper subsets, and A, the number of subsets, and B, the number of proper subsets. Okay, so in order to do that, what I really need to do every single time is to figure out what's the cardinal number of my set. So what is the cardinal number of this set A? 5. Okay, that's the goal first. You got to figure out how many things you have. So how do I find my number of subsets, part A of this problem?
You take the 2 and you put it into the power of 5.
You got it. You take the 2 and you put it to the power of 5. So what is 2 raised to the power of 5? 32. Very good. Yeah. And if you don't know, your calculator can do it for you, right? We're all good with that. If the numbers get pretty big, you might not know anyway. All right, it's 32. So how many proper subsets are there? 31. So it's 2 to the 5th minus 1, but it's 31. This is one of the places inside of my math lab that when you take a quiz and when you take an exam, if you miss part A, you're going to for sure miss part B if you're doing the part B part right? If you're just taking one off. So this is a place where I have to go back in and I have to award partial credit. Because if you miscounted and you thought that there were 4 of the elements in the set to start with, you're guaranteed going to miss both parts of this problem. But if you really understand that part B is just one less than part A, that's the point of part B. And I will go back in and I will fix those, okay? So I don't do it on homework because you have multiple times that you can try your homework. You got to figure it out on your own. You got 5 attempts, right? But on your quiz and on your exam, I'll go back in and I'll do partial credit on a problem like that. Does that make sense? Okay. Now, the next question does not actually list out all of the items. It gives us a verbal description in set notation. X is an odd integer between -9 and 4. So my advice is to let's write them out first. So what numbers would be included in this description?
-7, -5, -3, -1, 1 and 3.
Okay. Why are we not going to include -9? Yeah, it says between, right? It says between, so we don't include the ends points. 4 seems like a funny place to stop maybe, but it doesn't matter. I mean, it's an even number, so we just don't include it anyway. This is the set in listing method. So what are the number of items that are listed here? 6, or 6. Part A, how do I find the number of subsets?
Put it to the 6.
Yep, 2 to the power 6. We're getting bigger. 64 is it? Yes, it is. There's 64 subsets. How many proper subsets are there then? 63. Any questions? Okay.